years of industry experience with custom tooling and stencils. With that, Bill, please take it away.
All right, guys. Well, I appreciate everybody taking the time, and we're real excited to be able to put this on. And so we're going to talk about basically AGI's part in all of this. So AGI has been around since '94. We got our start basically doing solder pallets. And then about 15 years ago, we got into the stencil business. We purchased a deck franchise that was in Huntsville, and that's kind of where we got our start at. And stencils have gone very well for us. So, in respects to voiding, what we try to accomplish here is how do we design our different apertures so that we can minimize the effects of voiding or the occurrences of voiding. And then also, I want to take you through kind of the stencil manufacturing process, how we design our stencils, what materials our stencils are made of, what type of coatings we use to increase the transfer efficiency, and just kind of go over that aspect of our business and what we do. So when a customer wants to order a stencil, basically what happens is they're going to send us their Gerber data, and when they send us the Gerber data, we bring in that Gerber data through a program we call Gen Stencil. And what happens with Gen Stencil is it has basically industry standards with set definitions. And when the Gerber data is run through that, it automatically modifies apertures to those industry standards. So for instance, if you had QFNs or DFNs that you're worried about voiding or floating parts, it would automatically do an industry standard or a standard that we at AGI have set up from experience. So it would reduce the volume by 30% to avoid floating, and it would window pane in a 2x2 configuration. So that's one step. So for the standard library, but if customers through their own experiences have different aperture designs that they like to be implemented into their stencil design, then we create custom libraries or custom scripts for them. So once it runs that stencil through that design phase, it would bring in their script and apply their custom script to their stencil. And that's something that we do for all of our customers. Some don't mind using industry standards. That's what they like to go with. They don't want any input from themselves at all. They want us to do all of it. Some are very meticulous in how they like pads designed a certain way, and so we'll work with them to basically create those design packages in their own script file. So no matter what they send into us, it's always looking for those specific components and modifying the apertures in the way that they want to modify it so they get the stencil that they want. So it's a very good process, very quick process. It's very efficient. And one of the great things about it is, for instance, if a customer has a certain design that they like, if it creates area ratio problems or volume problems, the software actually flags it and tells us, so then we can come back and say, hey, for this particular design, I know you want a 5mm stencil, but you really need a 4mm stencil, or you're going to get bridging, or you're going to get excessive outgassing. So that's the kind of things that this software does and allows us to do. So outside of that, so once you get your stencil designed, how does it get cut? So laser technology has advanced over the last 10 years. It's much better than it was 10 years ago. So back in the old days, they had the old YAG lasers, and they had 40 to 81 micron laser beam diameters. So it was very rudimentary cutting. And what happened in those days, after you cut the apertures, stencils had to be electropolished because there were so many burrs and things left in the aperture wall. And it really created problems. especially as components started getting smaller and smaller and apertures got smaller and smaller to follow that. So the latest laser technology, now we're down to 15 to 19 micron beam sizes. So shorter pulse widths, frequencies, so they cut a much smoother aperture wall. And of course that increases your transfer efficiency, and that also reduces potential voiding issues. So this is the current laser that AGI has. So we've got two locations. We've got one in Huntsville, which is our main location, and we've got another location in Tampa, Florida. So we use T11 lasers. They cut roughly 30,000 apertures an hour. And you can see the beam diameter is 19 microns. Basically, we use pure oxygen, so oxygen burns a lot cleaner. And it also, allows you to have that much cleaner cut, much smoother aperture wall. Another thing that the T11 does is it allows us to do the large format stencils. So if you're manufacturing LED boards that are, very long, this laser is capable of cutting a 29 by 59 stencil, which is a huge stencil. But we have that capability here at AGI now, this T11 laser. And it also allows us to do welded steps. So, olden days it was either chem etch, and that was pretty much all you could do. And then it went into machine steps. And now the T11 laser, you've got chem etch, machine steps, and welded steps, and that's step ups or step down. So it's a very advanced laser, and it's really increased our capabilities here at AGI. So when we cut a stencil, so basically the program is loaded. The stencil is loaded into the laser foil side up. The laser follows an optimized path for cutting the image out. And what I mean by optimized is if you look at the bottom of the screen, basically the laser doesn't start at one point of the aperture wall, cut all the way around and stop before that point. Basically it starts in a dead area, and then it cuts the aperture, and then it overcuts. That way we don't leave any material behind, and we make sure that it's completely cut through and smooth. So there's even a method for how you're cutting out the apertures from your stencils to make sure that you've got a clean cut. So like I said, the stencil is loaded, foil side up, contact side up, it's cut. Once that's done, it's flipped over, then all the engraving and text is burned onto the stencil. One thing I don't have on this presentation is we are now able to actually burn a data matrix barcode, either on the stencil frame or on the foil. That's something that we're offering now, and a lot of customers seem to like that for traceability and stencil life. So that takes us into foils. So foil technology has really advanced. So, it used to be you only had a standard stainless steel stencil, and that's all you had. And so regardless of, what your beam quality is on your laser and how you're cutting it, you would still have issues because you had a 16 to 25 micron grain size in your metal. So there's a lot of surface area for your paste to stick to, and rough edges because of that grain size. And so really the only thing you had to do was, only option was to send it out to be electropolished. And that electropolish removed some of those burrs and other defects in the material on the aperture wall. Well, as we've advanced, we've gone into better materials. So now we're able to get a 1 to 2 micron grain size stainless steel. So you start getting that kind of material and also using advanced lasers to cut that material, you're already starting off with a very smooth seal wall. So you can kind of see the cross section here and what that fine grain looks like under magnification, and see that it's already very smooth. So with the small grain size on the foils, also with the laser technology, we no longer have to send these off to be electropolished. I think the terms they're using now are laser polished, but it's really just, with the beam size and the material technology. Um, so how do you improve that? So now that you're using a 1 to 2 micron grain size material, and it's very clean wall, well, how do you improve the transfer efficiency on these materials? Well, that takes us into the nano coating technology. So years ago, ASM came out with that, and it was originally designed just for reducing your cleaning cycles. And it was found that it actually coated the aperture walls and improved transfer efficiency. So at AGI, we currently offer the Nano Clear from Aculon. It's a very good coating. It can be applied in 3 ways: either wipe on, spray, or a aerosolized version of it. So it's a very good coating. It's something that we can apply, and we can even sell the customers the package to apply themselves. So over time, if they feel like the coating's worn off, they can reapply it. And here's a study on the different materials. So this chart is basically showing you how paste is printing through different materials. So, obviously the old laser cut stainless steel with the large grain size metals is on the low end of the chart here. And as you start going down, the laser cut fine grain in red, which is what we currently use, laser cut fine grain e-polished in green, laser cut stainless steel e-polished, which, like I said, is not really a practice that's done anymore. And then, of course, nano coated foils and nickel coated foils. And you can kind of see, for the most part, around that 0.55 area ratio. Most of them are all playing on the same ball field. So a lot of times, from 0.66 to 0.55 area ratio, you can get away with using a fine grain laser cut stencil.
Hey, Bill, just to step in here, we've got about 2 minutes left, and then we're going to have to move on. So.
Yes, sir. Yes, sir. So that's this is a very valuable chart when you look at this, and you can kind of compare the data of the different materials and the transfer efficiencies of the paste, through the different materials, and it's good for customers to see that, well, I know that 0.66 is the wall, and people start thinking below that we've got to have a nano coating. Really, it's, the new fine grain materials, once you hit that 5.5 wall, that's where you probably need to start thinking about the coatings. But prior to that, you're generally going to be okay. That is all I've got for this presentation. I thank you all again for taking the time and attending.
All right. Thank you, Bill.
Thank you, Matt.
All right. So next up, we have Adam Merling with Indium. Adam is the Assistant Engineering Manager of Technical Support based at Indium Corporation's global headquarters in Clinton, New York. Adam helps define and implement the vision, strategy, and long-term goals for the Americas-based Technical Support Engineering Department. He takes pride in providing leading-edge technical support for customers around the globe through SMT process optimization, material recommendations, and customer training. Adam has worked with small, medium, and multinational customers in Europe, Asia, and South America to provide them with the most efficient and cost-effective processes and products. He specializes in planning and executing customer and internal designs of experiments to give customers the data they need to ensure long-term reliability for their end product. Adam has over 5 years of experience in SMT troubleshooting. He is a certified SMT process engineer and regularly shares his expertise with a wide audience, both as an active blogger and as an author and presenter of technical papers to an internal audience. With that, Adam, please take it away. Adam, looks like you're still muted.
How about now?
I got you now.
Okie doke. So sorry about that, everyone. So I'm going to be talking about everyone's favorite consumable product, essentially solder paste. I know it smells great, looks fun, and everybody loves to work with it, right? So
Yes.
thanks. I also wanted to remind everybody that if anyone had any questions during the presentation, please use the chat feature. It just kind of helps everyone keep track of the questions as they come in. So to start off the presentation, I think it's best to always talk about the different kinds of voids. There are several different kinds. Mostly people are familiar with macro voids or planar voids, or voids that happen in the bulk of the solder or at the edges. Those are really the two main kinds. I've been starting to see more of the Kirkendall voids as I'm traveling around, which essentially is the submicron voids between the IMC and the copperland growth, which happens when there are higher temperatures than needed for the intermetallic diffusion rate. So this list actually comes to us from an SMTI presentation back in '06. So there is an updated one on one of the blogs on Indium's website. I was part of creating the Ishikawa diagram to kind of brainstorm all of the different environmental and all the different constituents that help create large ground plane voiding, from the stencil design, PWB surface finish, the environment, the paste itself, which I'll be primarily talking about today, the reflow profile, and PWB design. So it's really hard to pinpoint voidings caused to one particular area, but I'll be covering the solder paste responsibility in this talk today. So essentially here at Indium, we engineer our flux to essentially overcome overall void percentage. Customers want to see low void numbers, the size of the void particularly to be small, and then as far as the void position goes as well. We want to make sure that there's no opens or shorts, that it doesn't, when the outgassing is happening, it doesn't create any solder balls or any other defects or bridging that way. And one of the ways we do that is essentially by creating high fluxing capacity, and which promotes good wetting. So entrapped fluxes is essentially what can cause voids, or so high flux activity prevents the flux from being trapped, and it allows it to escape easier. So the graph on the left essentially is a log graph that shows the decrease in void content as the activity of the flux increases. And on the right, we show essentially the profile at 4 different time frames, decreasing the voiding at 3 different temperatures as well, 230, 235, and 255 C. As we go from left to right, the time increases, and higher temperature and longer time is definitely desired for most of the current modern flux chemistries available. So before outgassing has a chance to rear its ugly head, we really need to think about the oxidation resistance to help with the wetting and to essentially promote cohesion throughout the joint as everything's going through the liquidus stage. So you can see on the bottom right-hand side, we have on the left, essentially a solder paste and a solder sphere that doesn't fully coalesce. And the one on the right, it essentially swallows the solder ball whole and creates a homogeneous mixture. You can't even see the ball after it wets into the paste itself. That's kind of what we're striving for whenever we create a new paste, when we are focusing on voiding. QFN voiding. I find that everyone's very interested in the bottom terminated component, specifically the low standoff QFN in particular. So essentially we have many different experiments where we'll pre-reflow a board, components, fixtures, etc., to increase the amount of oxidation, to test the oxidation barrier of the paste, to get rid of the oxidation prior to reflow. So we have a 7-day and 14-day study on the upper left for 2 different QFNs, while also having 2 different surface finishes at a 7 and 14 day increments. Well, one is pre-reflowed and one is not. Essentially, the mean void percent would increase as you would expect after 14 days of conditioning prior to 7, but it's only a 2% voiding increase from 6 to 8% for this particular study, while the first one shows the 7 and 14 day for the pre-reflow condition for the main void as the same condition. We're always striving for voiding at less than 15% for the QFN thermal pad, and then 3 to 20% for the signal pads. So there's time above liquidus, and then there's peak temperature. So for this particular study, we had 2 different solder pastes. We had a 250 to 255 peak temp on the left of each graph, and then 235 to 240 on the right. You could see there's a mean of 7.3% and 11.6% voiding on paste 1, while there's 22.7 and 34.1% on paste 2. There's also corresponding photos to show you what those numbers mean in real time for the ground plane voiding. The aperture design was a 3x3 window pane to help those outgassing channels to promote the minimal voiding as possible on both solder pastes. And as most people suspect, as you put more paste down, you have a higher chance of having lower voiding. So on the left, we have 100 micron thick stencil, while on the right, we have 125 or 4 and 5 mil. I talk mainly in microns, but I'll make the conversion as best I can throughout the presentation. So essentially, the only thing differently that changed with this particular study is just changing to a thicker stencil. It's the same one as the prior slide, so the 3x3 up aperture design with the same paste that was paste 1 on the left. Now, throughout my travels, as stencil designs have changed and things are getting smaller and smaller, it seems that we're optimizing more for the smaller parts, while the larger parts are kind of sacrificed, so to speak. By going to a thinner stencil, sometimes the larger parts you end up with solder starvation voids. I've seen that quite a few times lately, at least since COVID started. I've had a lot of calls come in. Why am I seeing voiding on these components? I'm doing everything right. And then we do some of the math and just the volume's not there. So it's not that you're voiding, it's that there's just not enough solder paste or material there to bridge the gap. Or even sometimes some open vias that are plated, the paste will steal through those and create will create starvation void phenomenon. So sometimes we have to play a little bit and increase the aperture sizes to include that volume within those vias so that you can fill the vias and get your adequate voiding numbers. So as we continue with QFN design, there was a study where we essentially took 9 different stencil designs, printed them, and measured the voiding across all of the different designs. So there were different vents, 36 vias, no vents, triangle designs, window pane designs, and then we combined the triangle and the window pane. And the best design across the board is the one bottom in the middle. So the 9 square 36 via solder mask defined window pane. And this is kind of what I was talking about a couple slides ago with the via and pad voiding. So this is, for instance, more on a BGA, where outgassing can happen from the via into the bulk of the solder for the BGA. And if not looked at properly, one would just see that the paste or the ball just isn't wetting properly, or it's just not outgassing appropriately. or that the surface tension is just holding all the voiding in. But it's not coming from the volatiles of the paste itself. It's having some help from the epoxy that's not cured properly outgassing into the bulk solder. And that coupled with the normal outgassing phenomenon in solder paste creates these kind of large voids and creates the flux entrapment. And so plugging the vias become more common, but just be sure that they're cured appropriately. So one of the things that we've been investigating is the use of preforms to help mitigate to help essentially back up its solder paste counterpart. When you have a thinner stencil, to get those area ratios down for the smaller parts, sometimes adding in a preform can help with the voiding on the larger parts. So you can put them on the corners of the part, have them coalesce in. This also goes back to the oxidation barrier technology, so that everything, the alloys would be the same and it would create a homogeneous joint. You don't need to change your aperture design for your paste to get rid of the voiding in that instance. So for this experiment, essentially it used a voltage stabilizer. So we're printing into a cavity here, 150 to 250 micron in depth. So using a step stencil was needed. So in order to print the rest of the board appropriately, we had to, again, add the preform to help with the solder paste volume, because the thickness of the stencil was unrealistic from a step perspective for those interior apertures, while also keeping the leads at an appropriate volume and not skipping due to the different area ratio that the leads would see versus the overall ground plane for this part. And that concludes my time. Thank you.
Thank you, Adam. All right, so next up, we have MB Allen from KIK. MB is the manager of applications and sales at KIK and has been in the industry for 32 years. She is a member of the IPC and has published multiple technical papers. And with that, MB, please take it away.
Thank you. Can you hear me okay?
Yes, we got you perfect.
Perfect. Good morning, everyone, and thank you all again for participating today. I'm so happy to see both of the presentations prior to me, as I referenced both of those steps in part of the problems that we see associated to voiding. Today I wanted to talk about the issue itself, what the causes are, and you've heard some of that explanation now, the challenges and how profiling is a solution for that, and then further to the profiling, what all can you do on a continuous basis to have information and your trials and tribulations recorded. So as you've heard, voiding is a long time problem. We've seen this in the past. But we're seeing it more now, and as you heard referenced, we're seeing particularly on QFNs, LEDs, and other types of BTC components. And the issues, particularly with lead-free assemblies, at least that's what I've talked about in the past, but recently I've heard this come up with some companies that are still doing tin lead applications and experiencing voiding problems, again, on BTCs. With the miniaturization of components, we've seen the problem even more so. And, you know, our assemblies have changed significantly over the years. We're getting smaller and smaller for some types of PCBs, but we're also getting very large, densely populated boards with challenging components on those. And then when we talk about lead-free manufacturing, that process window has shrunk quite a bit. Two things that are also relevant to voiding is the reliability of the part, obviously in the field, and we don't have too much data on that. I'm not covering that in this session, but it certainly is something that needs to be taken into consideration when you're addressing voiding issue. It isn't just the problem that you see in front of you, but it is the long-term effect. And then what's the acceptability of the void itself, both size and quantity. There is some information available or some specifications for BGAs, but not necessarily for all components. So the cause, as you've heard, is attributed to the flux outgassing within the solder joints when the solder is at a molten state. And the cause of that could be any part of your particular process. It could be the solder paste, as we just heard from Indium. Stencil printing process is also could be a part of it, and how your placement is once your part is on the pad itself. But also a very big part of that problem could be attributed to the profile. You saw this graph earlier. I'm going to talk a little bit more about it as it relates to the reflow portion of the process. Believe it or not, those arrows relate to each of the areas of your profile that could attribute to the problem of voiding. So it isn't just one portion of the profile that you're going to look at when you're trying to find a solution. It could be the soak, both temperature and time over liquidus, your ramp rate, and your peak temperature. You heard a little bit about higher peak temperatures. We're going to talk about that as well. One of the challenges, or some of the challenges that we have when we're trying to reduce the voids, is how do we get there? You saw that there are multiple parts of your process that could be attributed to the voiding. So first you have to understand which portion of the process is causing the problem, and then how do I fix it? If there are so many areas of the profile that could be affected, how do I pinpoint exactly which one I'm going to focus on? And the reality is there is not one silver bullet for all of that. The density of the components, the density and the components themselves, you're looking at oxidation, as you would have heard with solder, but also you have to look at the components themselves, your storage and things like that, and then trying to find the right profile. And when you do find a good profile, maybe as it relates to the process window, does that profile have an effect or a negative effect on a specific component? So trying to find a solution across the entire PCB is always challenging. I have these two quotes that I show all the time, and the symbol for the music is because this is music to my ears. For so many years, the process window or the profile itself was really considered gospel. When you were given a process window, this is what you needed to abide by. And reality is now it is a guideline. But profiling in itself is really, it's a science, and it is the one variable that you can affect immediately. When you're looking at making a change to solder paste, you do have to go potentially through a qualification process again, and often you don't have the luxury of being able to take the time, or if you're a contract manufacturer, your customer may not give you that leeway. And if you are changing stencils, you do have a time delay from when you order it to when you get it. However, the profile is something that you can do to change what is going on, or at least do some trial and error in real time. So I mentioned that there are various parts of the profile that we look at that can be changed to try to eliminate or reduce some of the voiding. And those areas are soak, ramp to peak, or ramp to spike, depending on what you call it. There's also called a tent profile or a straight ramp. And in those, sometimes we look at lower peak temperatures, more commonly now higher peak temperatures, as you heard. Sorry about that. The ramp rate is also an area of the profile to focus on, but the time over liquidus is very important as well. And of course, your peak temperatures. With the lead-free materials, we do see high peak temperatures, and in some cases, the recommendation is to go even higher. And so then you have to take into consideration some of your more sensitive components. So there's a balance between making changes to your profile to reduce the voids to get a good solder joint, but you'll also have to take into consideration some of those more sensitive components. As an example, a plastic connector. If I'm elevating my peak temperature, it's really important that I know the specifications for the components on the board that could be affected by those changes. So when you are setting up to run a profile, one of the most important parts is that you look at the entire assembly. I said sometimes we're getting very, very tiny assemblies in the case of some medical devices especially, and reliability of those is so important. But then we have very large assemblies as well. So it's important to have a balance, and your thermocouples should represent your entire printed circuit board. And one of the problems, of course, with profiling is it's potentially destructive. So there are methods of attaching thermocouples that are non-destructive. We did a study with Rochester Institute of Technology on non-destructive profiling on BGAs as an example, whereby they created a calculator so you could put a thermocouple on the top of the BGA and know what the temperature was at the ball without doing destructive profiling. And that's available on our website, and you're more than welcome to download that. Some people have used that as an extrapolation also if they're doing bottom terminated components to understand the temperature at the ball without destructive profiling. So going into the profiles, one area that we look at is the soak. There are obviously different recommendations from different solder paste manufacturers on whether or not the soak is important or not. And really this is all going to be experimental for you to do on your own to decide on which is going to be the better solution. Very often we've seen with people that still want to maintain a soak in their profile that temperature, typically a recommendation is 155 to 185 for soak. We've seen that come up closer to the reflow temperature where that soak maximum temperature is up to 200 degrees C. So this is one area that you can experiment with. I've recently seen this where they've taken the soak even longer successfully. You have to realize that if you go too long, you can have other problems with your solder. But this would be a visual of what a longer and higher temperature soak would look like in your profile. Another area is the ramp to spike or ramp to peak. We see here that this has a peak temperature of 235 up to 255. Now you're getting a little bit hotter, but this seems to be something that is one solution that is very highly recommended to reduce the possibility of voiding. So this is what that looks like as a visual. You see that soak is gone. Again, your activation period that's going on right here is very critical to making sure that you're burning out your volatiles, but you're making a nice you're having proper wetting, but still reaching all your proper temperatures. And another area that I've seen experimentation we're going to a longer time over liquidus and a higher peak temperature. And then this number here, that 265, starts to get on the critical side because you do have to take into consideration your other components on the board, which is why the information is so important to gather about your entire printed circuit board. But I've seen much more success with some of these higher temperatures, and I've seen a lot of people start to make that shift to looking at a higher temperature for peak. And that's what that graph looks like. You see it's very similar to the prior one, but we do have a higher peak temperature here, and thereby eliminating some of the voids, particularly on QFNs. We talk about fine tuning, excuse me, and obviously when you're going through and you're doing all of the experimentation, you're making changes, and the changes are typically to the two oven parameters that you have the most control over, which is your zone set points and your belt speed. And so when you're doing that and you're making the changes, again, trial and error takes some time. So one of the things that we recommend is that you use software that's available for optimization. It takes some of the time away and some of those steps as well. And time obviously costs money. You're saving some money if you're using tools that are available to you to find a very quick solution within the specifications that you're setting up. So you do have different specs, as I mentioned earlier, but you do want to take into consideration all the components. One way that you can do that is by looking at each of the process windows for each of those components. Within our software, you have that capability of saying, okay, thermocouple 3, as an example, has a different requirement or a different peak temperature than possibly thermocouple 4. So a BGA, you might have one peak temperature requirement and an electrolytic capacitor another. So taking advantage of optimization tools really helps you find a solution to eliminate voiding much faster. And obviously the bottom line is saving some money. One thing that I have found over the course of doing this for so many years is that the knowledge that you gain by all of this experimentation is very important. Having the information in advance is important. Knowing your solder paste restrictions, component restrictions, allows you to make better decisions. One of the things that I think people don't consider also is their oven capabilities or limitations. When we switched to lead-free manufacturing, we were cranking those temperatures, and sometimes the ovens were still older and didn't have those capabilities. So you need to know what your oven's limitations are, but importantly is you need to know what they're set at. When you have an oven and you have it delivered, it is set up with a parameter for your zone set points, plus or minus X. So if it's set up for plus or minus 5 degrees, that means that that particular zone can be in spec with a range of 10 degrees, right? It can float 10 degrees. And if your process window is very tight, your oven could be performing perfectly, but you would be out of that process window. So it's important to know what how your oven is set up. And these are things that people don't often think about. I've seen ovens set up plus or minus 10 degrees. That gives you the ability of shifting between as much as 20 degrees. So your oven's working fine, but you may be missing some of the capabilities because you're going to drift and you will be out of your process window. So knowledge is important, but then the other part of that is taking advantage of the information that you've learned. You've gone through now, you had a problem with voiding, you've done your due diligence, your experimentation, and you've eliminated it. And then you go on vacation and someone else has the problem and you're not there to tap into. So one of the things that I find to be very helpful is customers that take the time and document what they've gone through, how they've rectified the problem, so that if the problem arises again, it's available to anyone in the factory. And it really also relates to similar types of assemblies, because while you may have had the problem on product ABC, when you run DEF, you may have a similar problem, and you could reduce the amount of time trying to find a solution by having that information available. It seems very basic, but people don't tend to document as much as they should, and it really helps across the factory. And obviously, Profiler is a tool that you can use to help you gain the information on the profile for each of your assemblies, and it should be for each assembly. It shouldn't be one profile for all. Of course, it can be that way. You can do some combining of profiles, but if you are having voiding problems, you're going to find that you're going to need be very specific to each assembly. Utilizing software tools can help you get there much faster. So in conclusion, right now we're seeing for voiding elimination, higher peak temperatures, and in many cases, a longer time over liquidus. The solder paste specification is a guideline. It isn't gospel, and you can change that specification and make it specific to your component. And make sure that you do a good balance across your various components on your board, not just be focusing on one component. Excuse me, and specifically for those that you're having problems with. And you can create separate process windows so that you can look for a solution that gets everything within their spec. And that concludes my presentation, and I thank you all for participating.
Thank you, MB. So next up, We have Keith Verdon from Heller Industries. Keith is a VP of sales for the Western US and Central America for 20 years. Prior to that, he was the VP of manufacturing for Heller Industries and has over 15 years of engineering experience. And with that, Keith. I think you're still on mute, Keith.
All right. Can you hear me now, Matt?
Gotcha now. Thanks, sir.
Okay. So basically, as far as voids, what we've seen is by eliminating the voids, you get better heat dissipation and solder void structure. We've also seen where reliability is improved. We just recently finished up a study with a power device company where they were seeing field failures. We took some of those boards, we ran them back through the reflow process, and they've been in a test now for over 1,000 hours without any. Basic theory of operation with standard reflow. If you reflow, you have solder voids. You end up with solder voids. With vacuum assist, you'll have your voids. You'll reflow and vacuum them, and then you'll end up with almost zero voids. The process is basically exactly the same as standard reflow. You'll have your convection zones in the beginning, and then you'll have your vacuum chamber where you actually go to full liquidus. What we find is that if you go to liquidus in this last convection zone, you bring the board into the vacuum chamber, you hold it at liquidus, and then you apply vacuum and remove the voids. What we've found is that you'll see this blue line where it talks about, where it shows the vacuum profile. What we found is that if you stair step this vacuum process, you'll eliminate a lot of solder splashing, because if you just take it from atmosphere down to somewhere between 5 and 20 torr, and you just come straight down, you'll pull those solder voids out so quickly that you'll actually pull solder out with them. So what we found is that if you do a stair-step process where you come down, you hold for a few seconds, you slowly pull those voids out, and then you bring it down to whatever this number is here, they'll slowly release those voids and pull them out. And what we're seeing is, about a 99% reduction in voids over standard reflow. Here, this is just a few examples of some components. This is some semiconductor, and all these are, what we'll do is we'll reflow it using standard reflow. We'll X-ray the component, and then we will reflow it a second time, and that's what this result is. So when it was reflowed the first time, we had a 30% void.
Keith?
Yeah.
I'm sorry to interrupt. I think you might be sharing the wrong screen. We can only see the preview version of your PowerPoint presentation.
Oh, really? Oh,
Yeah,
okay.
we're still on slide 2, Keith.
Oh, you are?
Yeah, when you mentioned blue line, I was...
Oh, okay. Let me,
All right, now we're on slide 6.
Oh, you are?
But
That's weird.
yeah, you're not in presenter mode.
And if you could also put this in slide or in the slideshow, so it's all on one screen, one big screen.
Yeah, Keith, if you just stop sharing and then start sharing again with maybe
Okay.
just on your desktop and then just
All
put it
right.
into full screen presentation mode, we should be good.
Okay. Can you see that now? The very first page?
Yes. Now just go down to the bottom right-hand corner and click on the little easel or projector screen right next to the 54%. Three over.
I don't know what's wrong here.
Tell you what, I'll just take over that and
Okay.
I'll run your presentation for you. Everybody should be able to see the full presentation now.
Okay.
Yeah, we can see it.
Can you see it?
Yes, sir.
Yes.
Okay. Go ahead and skip to. Keep going. One more. Okay, right there. Sorry about that, everybody. We'll speed through this. But again, this is what I was talking about. It was this slide here. Basically, what we do is go to this last zone. We take it right to full liquidus. We shuttle the board inside the vacuum chamber, pull vacuum, and then release the board. This blue line here is what I was talking about. What we found is that's most important is that during this during vacuum that you stair step it. So you bring it down, slowly pull out some of the larger voids. And then when you take it to whatever this is, the 5 to 20 torr, then that's where you release the rest of the voids. And if you do that slowly, it'll reduce any solder splashing. And then this profile here, it's not really flat. We're just showing basically time above liquidus here. So you'll still get, the profile shape that you need. You can go to the next one, Matt. This is the one that I was just talking about. So you can see that with standard reflow, there was a 30% void, and then after reflow, it was less than 0.5%. You can go to the next one. Here's another example. So you can see that there was 9 to 10% voids, and then after vacuum was applied, 10 torr for 20 seconds, less than 1%. Go to the next one. Here's a heat sink, again, 30 to 40% voids. And then what we did was, this was a double cycle, so we took it to 10 torr. We dropped it down, held it for 15 seconds, and then took it down again and held it for 5 seconds. The whole vacuum process takes somewhere between 30 to 45 seconds, because what you do is you're shuttling the board in, and since you're at liquidus, you can't just come flying inside the vacuum chamber, hit the brakes, and then start the vacuum process, and then you can't take off quickly. You have to, slowly speed up so that you don't move components around. So next one. Another example here, automotive application. We're seeing 20 to 40% voids, and then less than 1%. Skip one more, or a couple more. I'll just bypass these. Another one. Yeah. As far as edge hold conveyor, you can do it with either just a standard edge hold. Some customers still need the center board support, so the edge hold or center board support. And then if you're doing stuff like wafers and bumping, some customers just require a mesh belt only. You can go to the next one. You can go to the next one, Matt. This is just showing, again, stair step and repeatability. So you really need repeatability when you're coming down to the different levels. Go to the next one, Matt. Just try to get through this here. Next. No. And just in summary, by using vacuum reflow, you can definitely reduce voids. I guess the biggest thing that we're seeing is repeatability. Customers will come to us and they'll run along at 15%, 20%, and then their voids will jump up to maybe 30 or 40. So definitely, if for repeatability and reliability, reducing voids needs to be done using vacuum reflow, and that's really it, Matt.
All right, thank you, Keith.
Yeah.
And thank you to all of our presenters. Obviously, we went right up to our limit and we did not allow time for the questions. With holding to our 1 hour time constraint, I will say that we will go ahead and tally up all the questions that were presented ahead of time. We will tally up all the questions that were presented during the presentations, and I will send out a questions with answers from our presenters to everybody that did register for today's event. So on behalf of BarTron and everybody that presented today, we thank everybody for attending, and we look forward to hosting you guys in the next event.
Thank you very much. I appreciate it. This was good.
Thank you. Appreciate the feedback.
Thank you, Bartron, for organizing this. It was wonderful.
Yeah, thanks, Matt.
Great job, guys.
Bye-bye.
Thanks. Take care, everyone.
Tim, we'll be sending out the recorded video link per request. So I've made notes that you've requested it, and we'll make sure it's sent out to you.